Okay. Hi again. This is Brian Teitelbaum. I'm one of the application engineers here at AEE Solar, and I would point out that AEE started in business as alternative energy engineering back in 1979. And at that point in time, there was really no such thing as grid-tie solar, so everything was off-grid, everything was battery-based, and we've grown along with the industry to include all the other options for solar. But today's presentation is going to focus on off-grid systems in particular and battery systems in particular as part of that. So let's get started here. First, a normal disclaimer. AEE Solar is a distributor of goods and services used in the deployment of PV and wind distributed power systems. We are not accountants, attorneys, or code experts, although we do try to keep up with the latest codes. The information presented here represents the equipment and best practices that we are aware of. However, local and project-specific requirements can vary widely. So this is not, some sort of gospel. We're just trying to educate here. We're going to talk mostly today about batteries and specifically about lead-acid batteries. There are many other battery technologies that are coming to the fore these days, and a lot of them are still in development point. We're testing a few of them out. We're keeping very close tabs on them, and we will be doing a future presentation on different battery technologies that are available and how they compare to lead-acid and compare to each other. But, these days, lead-acid is still the go-to technology to use. It's still the most cost-effective option. It's still the most developed and the most applicable to applications that we do these days. So here's a basic explanation of the various types of lead-acid batteries. All of them have positive and negative plates and an electrolyte in there. Sometimes the electrolyte is an actual fluid or liquid, and that's called a flooded battery, or it might be in a non-spillable form, which is either a gel cell or an absorbed glass mat battery, as we show in the chart here. There's various advantages and disadvantages to each technology, and each technology can be applied to different situations depending on what you're doing with the batteries. So in the flooded section, there are maintenance-free flooded batteries. Very likely you have one in your automobile, for instance. They're very often lead calcium, but don't have a lot of cycle life. Maintenance batteries in flooded form are liquid batteries, and you do have to add fluid to them. You do have to service them, but they're designed for deep cycling applications, even up to 2,100 cycles at an 80% depth of discharge. And I'll explain depth of discharge a little more in a future slide. And then in the non-spillable forms, there are gel batteries where the electrolyte is actually in kind of a gelatin form and immobilized in that way. And then there's absorbed glass mat, which has these matting pieces between the plates, and the electrolyte is absorbed into the glass mat, so there isn't any actual liquid in there. And excuse me, each of these have various advantages and disadvantages to them. Battery capacity is measured in amp hours, and capacity of the battery is greatly affected by a variety of things. How quickly you discharge the battery or draw energy out of the battery. The quicker you draw energy out of the battery, the less apparent energy you can get out of a certain battery. And that's because a battery is essentially a chemical cell. It's an electrochemical cell. There's a chemical reaction going on in the battery, and if you are demanding a lot of power from that battery, that chemical reaction can only process it at a certain speed and only has a certain amount of efficiency at that. So as you draw higher degrees of current out of a battery, you will get less apparent capacity in the battery. As we show in the chart here, most batteries are rated at 20-hour rating, and we consider that 100% of its rated capacity, and they're often expressed as a C20 rate or C over 20 rate. But if you draw at a higher amp rate so that you drain the battery in 8 hours instead of 20 hours, you're only going to get about 88% of that C20 rate, all the way down to 1 hour. If you draw all the energy out of the battery in a 1 hour point, you're only going to see about 59% of the rating of a C20 battery. It's also affected by temperature, As batteries get cold, they can also deliver less apparent capacity. And conversely, if the battery gets hot, they can deliver more apparent capacity, although it greatly shortens the life of the battery, so we certainly don't recommend that. Batteries are essentially rated at 77 degrees Fahrenheit, and a C20 rate is very common. Poor maintenance will obviously affect capacity. Lead-acid batteries in particular need to be fully charged very often and not left in a partial state of charge for very long, or they build up high-density sulfate crystals in them that are very hard to dissolve. Essentially, you've lost active material in the battery at that point. And batteries will also self-discharge, stored for long periods of time without being charged. You know, as a battery sits, it'll just slowly lose its capacity to produce energy. And you see that even in an automobile. If you park your car for 6 months, you might have a dead battery at the end of that. And even if nothing's running, the automobile will still lose its energy. And when wiring batteries together, typically we have multiple batteries that may contain multiple cells, and we typically wire them in a series connection to get more voltage out of them, or in a parallel connection to get more capacity or amp hour capacity out of them. You know, each lead-acid battery cell is 2 volts. It doesn't matter how large or small the battery is. It could be the size of a dime or as big as a room. It's still 2 volts as a cell. But we put cells in series to gain voltage. A typical 12-volt battery, for instance, would have 6 cells in it. And you know, it's pretty obvious when you look at the battery. It has 6 entry caps for adding water on the top. A 6-volt battery would have 3 caps. A 4-volt battery would have 2, and just a 2-volt cell would have a single cap. So when we wire them in series, it means connecting the negative of battery number 1, for instance, to the positive of battery number 2, and so on. And as we connect battery cells in series, you know, each cell connected in series adds 2 volts. So in the example here, if you have two 12-volt, 220 amp hour batteries in series, you will yield a 24-volt DC 220 amp hour battery. So by putting cells in series, we're increasing the voltage, but we're not increasing the amp hour capacity of the battery. However, it's still increasing the amount of storage in the battery. Every time you add a battery, you're adding more potential energy storage. Now, if you wire batteries in parallel, the amp hour capacity is additive because you're adding more amp hour capacity, but the voltage remains the same. And in a parallel arrangement, the positives are connected to each other and the negatives are connected to each other. And so here in our example with two 12-volt batteries of 220 amp hours, in parallel, it'll yield a 12-volt DC battery at 440 amp hours. But as you notice here, it's still 5,280 watt hours, just like the 2 batteries in the series connection example. 2 batteries together is going to be a certain number of watt hours. It's just depending on how we hook it up, we get either a voltage gain or an amp hour capacity gain. Now, I want to point out something here very important in the diagram for the parallel connection, and we would say here output leads must be from the first and last battery for electrical balance. You'll notice here with these 2 batteries that the negative is coming off of the lower left corner and the positive is coming off the upper right corner, and that's very important that essentially the outputs from the battery bank happen in opposite corners of the battery bank. If you were to take, say, battery number 1, the one on the left, and have the output both negative and positive output to, say, an inverter or a DC load coming off that battery, most of the energy would come from that battery. The second battery is connected, but because of the resistances in the wire and the connections between the 2 batteries, it's going to be a higher resistance pathway for the electrical flow. So what's going to happen is you're going to get imbalances between the 2 batteries. The first battery is going to charge faster and discharge faster. The second battery is going to be lagging in both charging and discharging. And that's going to create an imbalance in the battery state of charge, which is going to shorten the life essentially of both batteries over time. So it's very important to have that kind of cross output, opposite corner output we call it, when you're putting batteries in parallel. Very important. important. In a series string, essentially, if you have one string of batteries, you just have a string, the positive comes out of one end, the negative comes out of the other, and the electrical path has to travel through all the batteries, so there's no imbalances at that point. Lead-acid batteries should be charged after every use. Ensure they're never stored in a discharge condition. If batteries are stored for extended periods of time, they should be charged approximately every 6 weeks, 6 or 8 weeks, somewhere in there. Don't leave them stored for too long because they will build up sulfate crystals inside. You do have to put in more energy into a battery than you've taken out. Batteries are not 100% efficient, and some of the charging current is lost in electrolysis of the water. You'll see bubbles in it. That's hydrogen and oxygen gas, and also loss to heat. There's some heat in the process. The charging should be temperature corrected. Batteries require a higher charge voltage when they're cold and a lower charge voltage when they're hot. So in order to get accurate charging, the charging source should be temperature compensated, and most charge controllers do have either a standard or optional temperature sensors, and they should be used if they are available. Now, if the batteries are in a controlled environment and they never see temperature swings more than, say, 5 degrees or something one way or another, temperature compensation is not that important. Flooded batteries need proper mixing of electrolyte to avoid stratification. Battery that's just sitting as a stationary battery, the electrolyte is a mixture of sulfuric acid and water, and the sulfuric acid is heavier than the water and will eventually settle out to the bottom of the battery, and the water will kind of float to the top. So you end up with very concentrated acid mix at the bottom and a very light acid mix at the top, and that, especially the heavy acid mix could actually corrode the plates, and it also distributes the active material unevenly. So equalization is done on them, and that's a deliberate periodic overcharge to prevent electrolyte stratification and equalize the voltage of lagging cells. Every cell is slightly different. So some cells are going to show, especially over time, are going to show a slightly higher voltage than other cells. Equalization means bringing it up to a higher than normal voltage point so that it allows greater charging of any cells that might have a slightly lower voltage, and it also creates a bubbling effect in the battery which mixes the electrolyte and prevents stratification. Most charge controllers have an equalized charge setting. Some can be set to manually equalize at some period of time, typically 28 or 30 days. And that's fine, although we found that manual equalization is really a better way to go, and should be done any time a battery is real deeply discharged, or if it's left in a partial state of charge, or just over a period of time because of stratification. Should be done at least 2-3 times a year, even better 6 or 7 times a year. Monthly is okay too. You don't want to equalize charge every day, but you do want to do it on a fairly regular basis. Battery voltages as relating to the battery state of charge. Batteries are going to show different voltages depending on whether they're being charged or discharged, or whether there's no load or charging source on them. But there is a correlation between voltage and state of charge. This chart kind of breaks down a few examples. For instance, in a 12-volt battery, fully charged with no load on it, it's typically going to read 12.6 or 12.7 volts DC, twice that for a 24-volt battery, and 4 times that for a 48-volt battery. If the battery is only 20% charged, meaning it's 80% discharged and there's no load, it's going to read a much lower voltage. If a battery is mostly charged but still charging, it's going to read a fairly high voltage. Equalization is going to be higher than that still. And then when you put batteries under load, it's going to drag the voltage down. So a fully charged battery under a heavy load is still going to show fairly low voltage even though it's fully charged. And a battery that's only 20% charged under heavy load is really going to show low voltage. As a matter of fact, in the chart here, we're showing, for instance, in a 48 volt at 40.8 volts. Well, most inverters will shut off at 43 or 44 volts, so that's going to be a condition where it won't even power the load at that point. Charging voltage must increase as battery falls. If batteries are in a cold location, the voltage must go up, and the temperature compensation of the charge controllers typically do that, or the temperature sensors of inverters if you're using the inverter to charge the battery through an AC source. Same way, it also needs to have temperature correction. And it's very important to have a battery monitor. Even though you can read voltage and you can take hydrometer readings of the electrolyte and whatnot, it's really a battery monitor is really the only way on a day-to-day basis to really keep track of the charge and discharge of the battery and where the status of the system sits. Keeping track of amp hours, voltage, and temperature to determine the state of charge. There's a number of types of equipment out there to do that. You know, system-based equipment such as the Outback FlexNet DC, which has its reading out on the Outback Mate, is one way to do it, or separate amp hour meters such as the Bogart Trimetric or Pentametric, and there are many other types. But some form of battery monitor is essential for off-grid systems. Without one, you're just kind of flying blind. It's kind of like having the fuel gauge in your car. It's not essential to the operation of the car, but if you don't have one, you're going to find yourself stuck on the side of the road from time to time. So it's the same way with an off-grid system. So battery monitors should be included in any kind of system that's off-grid and relying on the batteries. And checking the battery voltages or specific gravity of the batteries during any maintenance call is always the first thing to do, is to go to the batteries and make sure that they're still in functioning condition. And before checking any other potential problems that may be in the system. Depth of discharge. Well, batteries are often called storage devices, and it's kind of a misnomer. Really what a battery is a production source. It produces electricity through a chemical reaction, and that chemical reaction is reversible. If you apply energy to the battery, you can reverse the chemical compounds and return it to a initial state of charge to where it can produce energy again. But depending on how deeply you discharge the battery, you're going to get a certain amount of lifespan out of the battery. Essentially, a battery can only produce a certain amount of kilowatt hours over its lifespan. So if you lightly discharge the battery, say every day, you're going to get a lot of years out of it. If you heavily discharge the battery every day, you're going to get a much shorter period of time out of them. But it's going to be roughly equivalent in terms of the amount of kilowatt hours that the battery has produced. There is some variation. Low depths of discharge over a period of time will deliver longer service life than heavy discharges for short periods of time. And this chart kind of shows a comparison at, say, a 5-hour rate, which is a pretty heavy discharge on a battery, but showing depth of discharge and how many cycles you would get. So, for instance, at only a 10% daily depth of discharge, you might get 6,200 cycles out of this particular battery. But at a 50% daily depth of discharge, you're only going to get 1,800 cycles out of that battery. And if you did that every day, of course, that's 365 days a year, so you can easily calculate this as number of years. Shallower cycles will enable longer life in general. And usually for off-grid systems, we try to keep it to somewhere around the 25% depth of discharge on a daily basis. And that has other advantages, for instance, giving us about 3 days of storage if there's no charging sources and that kind of thing. So it often works out at that point. And that seems to be a pretty good sweet spot for cost effectiveness of the battery. Never leave batteries discharged for more than a few days. The electrodes will gain a coating of sulfate crystals, and the longer that they remain in a crystalline form, the harder they are to redissolve back into the electrolyte. And they get to some point in hardness where you really can't do that. And what typically happens is over time they just build up on the plate and they're blocking the active material on the plate. So you've lost capacity of the battery at that point. Typically, also over a period of time, they will slough off and settle to the bottom of the battery, but that is still active material that was manufactured into the battery that is no longer available for the chemical reaction to produce the energy. So you don't want to do that. You want to make sure your batteries stay charged as much as possible. Obviously, in an off-grid situation, you may go through many days of cloudy weather where you don't have any charging. You're going to be discharging the battery. But you don't want that to go on too long. You may need to run a generator or have some other power source come in at that point to recharge the batteries. And battery watering is a very important thing. Only add distilled water or deionized water to lead-acid battery cells. No well water, no tap water, no stream water, creek water, no ponds. It needs to be very clean water. Obviously, any minerals or other contaminants that are dissolved in the water are going to affect the chemical reaction in the battery, so we don't want to do that. Typically, you don't add any acid or electrolyte to battery cells. They come from the factory with the proper amount of acid in there, so we're just replenishing the water that's lost through electrolysis of the water and through evaporation. Certainly, if you were to, say, spill some electrolyte out of the battery, it might be appropriate to add some acid at that point, but that's a pretty rare situation. You don't really want to have an acid spill, so it's not something that hopefully will come up for you. A fully charged battery, the electrolyte level should be filled to approximately 1/8 of an inch below the bottom of the filler well. After you remove the cap, you can see the bottom of the well there. But don't overfill the batteries. When they're charging, the electrolyte will expand, and you could have an overflow, which is going to be not only a mess, but a loss of active material from the battery. As long as the plates are not exposed, you don't really need to add water until you've fully charged the battery. However, if the plates are exposed, do add some water to the discharged batteries to just above the plates, but don't fill it all the way before you charge it. You know, it is going to expand, so you don't want to have an acid spill. Now, single point watering systems can make this much easier. Instead of having to remove each cap of the battery and pour water in there, there are systems that connect all the caps together through a series of small tubing to a central water reservoir, typically a 5-gallon reservoir that's hung on a wall just slightly above the height of the batteries at the top of the batteries, and there'll be a little manual valve you turn on. It allows water to flow to all the batteries. There's typically a little wheel in a clear window that indicates water flow. These systems are not completely automated. You do need to manually turn them on and turn them off, and the reason for that is that they're based on replacement caps that have float valves in them. And a float valve, as anyone knows in the real world, can actually, stick. There could be some corrosion in there or some dirt in there, or it can just stick somehow, and you could have an overflowed battery and an acid spill. So somebody needs to be on hand to monitor the system and make sure it's functioning properly. But it's still a great help to be able to just, to turn on a valve and have all the batteries watered, and then when you stop seeing any water flow into the batteries, you can turn the valve off for the next application. And we carry those for a variety of battery types, and they're often supplied by the manufacturer. Battery safety, very important. You're dealing with sulfuric acid solution in the battery. It's very corrosive. It's very damaging to skin and eyes if you get it on you, and very damaging to clothes if you get it on your clothing. I would warn you, if you're dealing with lead-acid batteries, to never wear a nice pair of blue jeans. It seems like blue jeans only have to look at batteries before they get holes in them. It's just kind of an odd thing. You think you're being really careful, and then you put the blue jeans through the wash, and you'll see holes all over them. So wear some wool clothes or wear some acid-resistant clothing. Hazmat suit, for instance. Certainly wear goggles or safety glasses or a face mask. Very important when you're dealing with batteries. Keep all sparks, flames, or metal objects away from batteries. It's a good idea to not wear any jewelry, especially hanging necklaces and other things, or rings on your fingers that are metallic. You don't want to do that because you're dealing with some live posts, and you can certainly hurt yourself by having metal contact live parts. So make sure you're not doing that. Acid spills can be neutralized with baking soda, either baking soda powder just spread in, or you could have a baking soda solution in water to help neutralize acid spills. Make sure the vent caps are securely in place before charging. The vent caps will prevent a lot of acid mist from escaping from the battery while it's charging. which can make a mess and cause a lot of corrosion of cables and whatnot. And of course, proper ventilation is very important to prevent gas buildup. The primary gas we're concerned with is hydrogen gas, which is very flammable in the presence of oxygen. Obviously, it produces water when it burns. It does take about a 3 or 4% concentration of hydrogen to be explosive, but we don't want to get anywhere near that point. However, hydrogen gas is also very light, so it's very easy to dissipate through proper venting and vent at the topmost part of a battery enclosure or a battery room. Essentially, the hydrogen will try to get out into the atmosphere because it wants to go up in the upper atmosphere anyway, being very light, as opposed to something like, say, propane gas, which is very heavy and would sit and pool on the floor. Hydrogen doesn't do that. It tries to escape through the topmost place. But make sure you have good ventilation. You also can deal with hydrogen sulfide gas, which is poisonous. So it's that rotten egg smell. You don't want to have too much of that because that is poisonous. Periodic inspections and cleaning of the batteries is very important. Batteries need to be kept clean. Tops of the batteries should be wiped down with a rag or a cloth and a baking soda solution to keep them clean. If you have too much electrolyte buildup on the top of the batteries, it can form electrical paths that can cause short circuits and also obviously corrode wire connections and whatnot. Make sure the caps are tight. Make sure all the connections of the cables are tight. Loose connections can overheat and cause meltdown in the connections, so make sure they're good and tight. It's a really good idea to use a terminal protector on the terminals to prevent corrosion. This is particularly with flooded batteries. Petroleum jelly works well, although it's kind of messy. There are products on the market specifically for this purpose, and we also carry that, so you can get that through us. And again, using a solution of baking soda and water to clean any acid residue on batteries or the corrosion of the terminals. But don't allow any of that solution to enter the battery, obviously. Not only would that neutralize some of the active material in the battery, but it would likely cause a fairly violent bubbling of it. And hopefully you have your safety glasses on, but hopefully you don't get anything in there. So make sure you don't get any baking soda inside the battery. Batteries need to be housed properly. It could be a pre-made enclosure, such as we're showing here from a couple of manufacturers. It could also be a built system. Very often battery boxes are built with plywood and lumber. Should certainly be coated with heavy-duty paint. And the battery should either be in a tray or the bottom of the enclosure should be sealed in some ways to keep acid spills contained. Battery enclosures must be ventilated. Active ventilation may be required for flooded batteries in hot or tightly enclosed spaces. If there's a lot of gassing in the batteries, you'll get corrosion if you don't vent it properly. A 2-inch pipe going straight up and out the roof, or up and then out through a sidewall, as long as it's much higher than the battery compartment itself, will evacuate most of the hydrogen gas. But very often in situations with a lot of gassing with large battery banks, you do have to use active ventilation, essentially a battery vent fan. Zephyr is a company that we carry that provides those, so those are available to do that, to vent any gases out. These batteries we're showing here in the lower right are the Outback REE batteries, and they are sealed. Now, sealed batteries can still, under occasion, let out gases. So all batteries need to be vented, although it's extremely important for flooded batteries to have very good ventilation. Obviously, batteries need to be kept away from people, pets, and falling objects. People that aren't actually servicing the batteries or authorized to work with the batteries. You don't want to have kids and pets and metal objects falling on your batteries, so make sure they're well protected. If you're doing a stacking system with batteries, make sure that it meets any applicable seismic requirements for your region. A lot of the pre-made battery enclosures and some of the industrial grade batteries have earthquake rated racking, so that may be important to you depending on where you're located. And having circuit breakers or switches help improve the safety when using servicing batteries. Certainly, you want to be able to turn off any charging or discharging sources of batteries if you're removing any cables or doing any kind of replacement of batteries of that. Make sure your terminals are deadened at that point. Okay, we're going to get a little bit into battery bank sizing here. Typically, we look at what the daily energy consumption is. Again, working with off-grid, we're dealing more on a day-to-day basis. This is a lot different from grid-tie systems, which are basically just trying to produce a certain number of kilowatt hours over a year. It's averaged over a year. In an off-grid situation, we're really dealing more day-to-day on that. So we really have to have more, figures that are more attuned to the day-to-day operation of the system rather than just yearly energy production. So what we look at is the daily energy consumption, and this is typically an average day. Very often we calculate for a week and divide by 7 because not every load is necessarily run every day, but we want to get some sort of average daily consumption. And batteries are rated in amp hours, whereas energy consumption is rated in watt hours or kilowatt hours. So we typically need to make a conversion there to determine our amp hour daily consumption. We have to add up our DC loads and convert to amp hours, and we add up our AC loads and convert to amp hours. Also keeping in mind that when you're converting DC to AC through an inverter, there's an efficiency loss, so we have to make sure we account for that. So amp hours is the watt hours divided by the battery voltage. It's usually much easier to convert kilowatt hours into watt hours to make this calculation. So I encourage you to do that. So the required battery capacity is going to be the average daily consumption times the days of autonomy. And days of autonomy means the number of days that you might expect to have to use energy from the battery when there's no sun out or no other charging sources. So the battery has to carry the load for some period of time if there aren't any production sources. And then you divide that by the recommended depth of discharge. And you have to account for temperature multiplier. If the battery is not at somewhere around 77 Fahrenheit, there's going to be a variation in the battery capacity. So you have to keep in mind the temperature multiplier. So we end up with a number of our required battery bank capacity in amp hours. And then when we're looking at specific batteries, each battery is going to have a specific capacity as a unit. Whether it's a 220 amp hour battery or a 350 amp hour battery or an 800 amp hour battery or a 2000 amp hour battery, whatever we're looking at, we need to see how many of those we need to have the required battery bank capacity. Now, we don't want to have too many parallel strings. Ideally, you just have one string of batteries in series. The advantage of that is the current must flow through the entire string of batteries, and even if there are strong and weak batteries in that string, they're all charged and discharged on an even rate since the current is flowing through all of them. As soon as you put two strings in parallel, you have slightly different paths. And there's no way to have any string exactly equal in resistance to any other string. Plus, there's changes or variations in the resistances of the cables connecting them. And electricity is always going to take the path of least resistance. So whatever pathway between the negative and the positive post of the batteries to the outputs has the least resistance is going to be where the majority of the current flow is going to be. Now, as current flow goes up, the resistance increases, or the effective resistance increases, and will then start to equal a higher resistance pathway, and there will be some equalization. But still, you do get some imbalance with any parallel stringing. We typically limit that to no more than 3 parallel strings. When you get into 4 or more parallel strings of batteries, you start to get so many imbalances that it greatly shortens the life of the battery. There are some ways around this. Big industrial systems use huge wall-mounted bus bar systems and have equal cable lengths to each string of batteries. You might have 6 or 10 strings of batteries. You know, one string of battery might be 3 feet away from the bus bar, and one might be 15 feet away from the bus bar, but all the cables connecting to that bus bar are going to need to be 15 feet long, so the resistances are as equal as possible. So it's possible to do that. It gets very complex, but you know, ideally in most systems, you want to try to aim for a single string of batteries. If you need more capacity, just go to a larger battery. Very often, though, it's more cost-effective or easier to maybe move around or some other reason to have parallel strings. So you can do, you know, 2 parallel strings or even 3 parallel strings, but I would not recommend doing more than that. Then we look at the battery bank voltage, and we look at the voltage of each battery, and that tells us how many batteries are in a string. So for instance, if we're using a 6-volt battery and we have a 48-volt system, you're going to need 8 of those 6-volt batteries in a series string to make 48 volts, or 4 of those 6-volt batteries in a series string to make 24 volts. So then we look at the batteries per string times the total parallel strings, and that gives us our total batteries. So for instance, if we were, say, looking at say for instance, a 700 amp hour battery bank at 48 volts using an L16 battery, which is roughly rated at 6 volts and 350 amp hours, that would be 2 strings of 8 for a total of 16 L16 batteries. And you may, you know, when you're sizing a system, you may need to try multiple different battery sizes. You know, maybe take a look at L16s, take a look at a larger battery, maybe look at some sealed batteries. Depending on the application, depending on your customer's needs, you're going to, and the cost of batteries, you're going to want to compare several different scenarios and see what's the best for the application. Okay, we're going to get into some more general off-grid sizing information here. Now that we know a little bit about batteries. This is somewhat of a rough block diagram of a typical off-grid power system. So we have in the upper left there, we have a solar PV array, typically several series strings of PV modules that are then combined in a combiner box. The output of that goes to a DC breaker, then to a charge controller, to another DC breaker, which then goes on to the battery. Everything in that green line there is essentially what would be included in a what we call a power panel or a DC distribution box, switchgear hardware. Although often the DC breaker for the inverter is also included in there. We're not showing that in the green box. The battery monitor might also be part of that, or it might be remotely set. Then we're drawing DC power off the DC buses, going through a main breaker to the battery-based inverter, which is then running loads in the load center. And a generator input might be added to come into the battery-based inverter to act as a secondary charging source for the batteries and a way of running loads if the battery capacity is not keeping up with the loads in the system. And then, of course, any other charging sources, wind, micro hydro, anything else that you can use to help charge batteries are often a great help in off-grid systems. It's not always sunny, but typically when it's not sunny, the wind might be blowing or the rain might be coming down. There might be other ways of producing energy to make the system more stable. So there's a bunch of data you need to collect when you're figuring out a design for an off-grid system. We need obviously to know what the average daily consumption is to get an idea of you know, how large the system is going to need to be and what it needs to supply. The whole point of these systems is to run loads. So we need to know what those loads are, and we need to account for those quite well. So, you know, you want to look at each load, typically make a list, and I'll go through that in a little bit here. You multiply the power draw of the load by the number of hours it's used each day to figure out how much energy it's going to consume on a daily basis. It's good to know if the loads are seasonal. For instance, if a load is only used, say, in the summertime, like, say, air conditioning, well, there might be a lot of power being produced in the summertime from the PV array because of long days. And that might not affect the batteries that much because the air conditioning might only run during the day. It might not actually draw from the batteries. Whereas the loads that are run in the wintertime are more commonly drawn off the battery because the days are shorter and there's typically more inclement weather. So seasonal variations are important to keep an eye on. For appliances, if they have an Energy Star rating, that's great, because you can often look it up on the Energy Star site and figure out exactly how many kilowatt hours a year it uses and divide that by 365 to get an average daily consumption. We need to know what the peak load is. How many of these appliances need to run at the same time or are likely to run at the same time? What is that peak load going to be? We need to make sure our inverter is sized for that. So we don't have too small an inverter for a big load. And of course, we need to know the characteristics of the loads too. Is it 120 AC, 240? Is it 50 hertz or 60 hertz? Foreign countries have to have different power grids. We need to make sure we match the inverter and the equipment to the actual power needed, or variety of power needed, depending on where it is. We have to look at our days of autonomy, and that's how many days in a row we need to run the loads with little or no sun. Don't neglect heavy snow. The reason for that, snow may cover a PV array for a number of days if nobody's available out there to clear the snow off, or if the snow is on the roof and not accessible. So, to keep that in mind, that there might be periods of time when there really isn't a lot of solar production, and the battery needs to carry you through that, or a backup generator may have to be used. And when we're sizing a system for off-grid, we're looking at sun hours per day during the darkest month of the year, not the yearly average. When you're doing grid-tie systems, you just need to look at a yearly average, and because you're producing bulk kilowatt hours that are accounted for over a year's time. Again, with off-grid, we're dealing more on a day-to-day basis, and we need to really size the system to be operating in a worst-case scenario, not just an average scenario. So that's real important to do. Now, you may, say in December, you may want to decide to actually run the generator more, although running generators is very expensive, and with PV so cheap these days, you really should size the system properly for the darkest month. So there's a variety of ways to do this kind of load analysis. We do have some worksheets in our catalog. We also have a Excel version of this worksheet that we can email to you to work out. You can certainly create your own. Essentially, you're just listing what all your loads are. You're listing how many watts each load takes. You're multiplying that by the number of hours per week that that load is run, and we end up with a watt hours per week, and then we can divide that by 7 to get an average per day. The worksheet also accounts for inverter efficiencies and can convert it to amp hours based on battery voltage. It's very handy to do. I recommend people use these kind of worksheets, at least in the beginning, to kind of learn the process. After a while, it'll become a little bit more intuitive, but the worksheets are very helpful. One thing to pay attention to is what we call phantom loads. These are loads in a house, typically small loads, but they're loads in a house that are plugged into electrical outlet or draw electricity. Even when the unit itself or the appliance or the stereo or whatnot are not being used, many of these things actually draw small amounts of power. And 1 or 2 is typically not a problem, but if you look at a typical house, you might have a whole bunch of these kind of phantom loads. This list was put together by the California Energy Commission as just one example. This is not, this is showing a certain amount of watts per loads, like a desktop PC or an LCD television or a plasma TV. These are somewhat averages of what's out there on the market. It's not necessarily definitive to all of these individual things, but as you can see, this adds up to quite a bit. I mean, with all of these plugged-in things, a garage door opener, there's a microwave oven that has a clock on it, a coffee pot that has lights on it. Anything that has a remote control is essentially the circuitry is on in the device. It's just waiting for the remote to tell it to operate. So these things can add up. And in this example, you add all these things up, it's about 123.5 watts. And you run that for 24 hours a day, that's almost 3 kilowatt hours a day. That's a significant amount of energy. And so Very often with off-grid systems, we're very diligent about putting many of these things on switches or switchable plug strips. Turn them off completely when they're not in use. Highly recommend that. However, some things you can't do that to. It might be a telephone answering machine. It might be a satellite dish receiver, for instance, where you turn it off, you lose all your programming. There's a variety of things that you're just going to have to account for as the energy mix. Other things, video game console, for instance, put it on a plug strip, turn it off when it's not in use, and therefore it won't be something that's drawing energy. Very important point to keep track of. And when you're designing a system, there's a whole bunch of options that you're going to need to go through and choose depending on the application and your customer's needs. There's a variety of different batteries, flooded, sealed batteries. There's a bunch of new technologies coming on, sodium ion, which is like a saltwater battery, or a lithium ion. Like I say, there's a lot of new technology coming in. Nothing is really fully settled and developed yet, for instance, for the market, and nothing's really competing right now for lead acid, especially in terms of price. But certainly we're paying attention to all these technologies. We're testing a few of them, such as Aquion's sodium ion batteries, and we're certainly working with Tesla to develop their battery technology too. So there will be other forms of technology, but right now today we're still really dealing with lead acid. But there are maintenance considerations, and that might be a choice to use a sealed battery rather than a flooded battery if there isn't a competent person to do maintenance on the site. Shipping and storage requirements are all going to go into this effect too. You need to look at what's most applicable for the voltage that you need on your battery bank. 48 volts is generally the most efficient and cost-effective for AC systems over 2 kilowatts. So most off-grid home systems, or anything over about 2 kilowatts of either inverter or PV power, is typically done at 48 volts these days. I think we're going to be moving into some higher voltage with battery designs such as the Tesla, which is actually about a 350 to 450 volt battery. That has its own issues code-wise, but I think that's what we're going to be moving into. But right now, 48 volts is really the most cost-effective and most efficient at the current time. There's a variety of different charge controllers available. Pulse width modulation or maximum power point tracking are two different styles of charge control. They require different applications or are used for different applications with different types of PV modules. So it's really important to look at that and choose the right thing there. There are many pros and cons to each one. MPPT controllers are generally more expensive, but they also do a much better job at harvesting energy from solar panels, so you can typically get more charge off the same number of modules. And depending on the module type, PWM controllers require what we call nominal rated modules, either 12 volt nominal or 24 volt nominal, or multiples of those in series to get higher voltage. And whereas MPPT can convert essentially any voltage above what the battery voltage is into proper battery charging voltages, so it gives you a lot more control of the use of modules. Energy production sources, obviously PV modules, very reliable, predictable energy source, and relatively inexpensive these days compared to what it used to be. Wind turbines are an excellent supplemental source of energy in windy areas. It's certainly any time you can supplement a production to an off-grid system, you're going to make that system more reliable, more robust. So looking at off-grid wind turbines is a good idea. If there's water flowing down a hill that you can put in a pipeline and run through a small microhydro turbine, that's an excellent source of producing power for an off-grid house. Very reliable, often run 24 hours a day, maybe even year-round. But even if it's seasonal and just occasional, it's going to be producing energy typically at times when there's not enough sunlight to get the PV to work at full output. And engine generators are used almost always as backup systems. Might be diesel or gasoline, although propane is really the most appropriate for off-grid houses, since most off-grid houses already have propane for things like cooking and water heating. They're noisy, but they're predictable. In a pinch, you can certainly get power out of them. Unless you use biodiesel, it's not a renewable source, however, and they're noisy and polluting. Okay, so sizing PV arrays for off-grid systems. Again, we want to look at the peak sun hours during the darkest month of the year. We have a set of maps in the back of our catalog for the whole world that show average peak sun hours in the darkest month of the year on the map. These maps are not the average of the year, so they're not appropriate to use for grid-tie systems, but they're very appropriate to use for off-grid systems. And the darkest month of the year might be different worldwide. I mean, here in the U.S., it's essentially, you know, December or January, but there are other places in the world where the darkest month might be in the middle of summer because of a monsoon season. So these maps take that into account and are very good, very quick reference. Obviously, the detail for a specific site is not real close, but you can still get a pretty good idea, say in, you know, central Mexico or central United States, of what your darkest month peak sun hours are. You can also, of course, use the NREL Redbook. The National Renewable Energy Lab has some extensive data over hundreds of sites in the U.S. and even in the world, you know, showing what the amount of peak sun hours are at different months of the year. The PVwatts Calculator online, I highly recommend using this as a source of calculating system design. But again, you have to pay attention to the darkest months. So for instance, if you look at this chart here, you look at December, there's only 1.84 peak sun hours in that month. You know, that's going to need to be a fairly large PV array to make enough energy to carry you through at that point, as compared to, say, July at 5.87. Now, the average, obviously, you would use for a grid tie, but you're going to look for the darkest months for off-grid. So I have a whole sizing worksheet on figuring out off-grid array sizing in the catalog. Again, this is a great way to kind of learn your way of sizing systems. I highly encourage using it. It's fairly complex, goes into a lot of details, but it's a really good learning source for that. When sizing PV arrays for PWM controllers or pulse width modulation, we're dealing essentially with amps at that point, not wattage from the array. So we need to look at the daily consumption in amp hours, multiply it by 1.2 for losses through the battery, divide that by the kilowatt hours per square meter a day, or the peak sun hours, and we get our required array amps. And then you select the PV module, look at the peak current amp rating, and match that up to figure out how many strings and how many modules you're going to need. If you're using a 12-volt module, which is a 36-cell module, and it's a 12-volt system, there's only one module per series string. But with that same module in a 24-volt system, you're using two in series in the series string. 48-volt will be 4 in series. And there are 24-volt nominal modules, and a 72-cell PV module is considered 24-volt nominal. So in a 24-volt system, you just have one in a string at that point. So then you need to look at your total number of strings and the total string length, which will give you a total of modules that you will need. MPPT charge controllers are somewhat easier to calculate because you're really just dealing with wattage at that point, because it's able to essentially convert higher voltage than the battery into more charging amps, and it's working on tracking the maximum power point of the module in terms of a wattage output. Most MPPT charge controllers on the market these days are rated to 150 volts maximum, which means that you can only use up to 3 typical 60-cell modules in a series string before you start to bump up against that 150-volt limit, especially in cold weather. And if it's a 48-volt system, you really need to use modules in series strings of 3 for 48 volts. There are some controllers that go up to 200 volts. You can typically use 4 modules in a string. Some that go up to 250, you can often use 5 modules in a string. You certainly have to do your temperature calculations to make sure you don't exceed the voltage rating of the controller. MPPT controllers are current limited. An 80 amp controller is going to limit its current to 80 amps. So even if you have more potential from the PV array, it's essentially going to limit you to that 80 amps of output current. And 80 amps at 48 volts is roughly 3,840 watts. And as a rough calculation, I basically figure an 80 amp controller will do a 4,000 watt array. When a battery's charging, it's typically higher than 48 volts. So 80 amps times, say, 50 volts DC is about 4 kW. But as you can see, if you only had a 24-volt system, 80 amps at 24 volts is only 1,920 watts. So that's half the wattage with the same controller. It's another advantage of doing 48 volts is you can use fewer controllers for a certain size PV array. PV arrays do rarely put out their full rated power except at high altitude sites. But you might have things like snow reflectance, very cold weather, other things where you'll see full output. But typically it's slightly less than what the rating of the module is. You obviously need circuit protection on every circuit in a system, especially important with battery systems because batteries have the capacity to dump thousands of amps into short circuits, for instance, so you make sure that all your wiring is protected with properly rated DC fuses or circuit breakers. Most modules have a 15 amp circuit rating, so individual module or a string of modules in series would need to be on a 15 amp circuit. As we see 60 cell modules pushing the 300 volt range, we're starting to see 20 amp ratings on those modules. So I think the 15 amps is going to be even less common in the future. We're going to start seeing 20 amp module circuits. Make sure the breakers are rated for the maximum voltage of the string. Might be up to 600 volts. All array circuits going to each charge controller must have a separate and isolated feeder to the charge controller. Each controller has its own PV array. It's isolated from other controllers and other PV arrays. There are a few controllers out there that you can actually gang up together on the same array. Midnight's Kid controller, for instance, you can use. It's a 30 amp controller. You can use 2 of those to get 60 amps on a single array. And some other controllers are starting to design those into their systems too. But in general, you have a PV array to a charge controller to a battery with overcurrent protection in between, and then if you need to have multiple controllers, they need to have separate arrays and separate wiring. You can't really combine them together. The charge controller array breaker and disconnect serves as a battery breaker. You need to be able to, the charge controller is considered a non-permanent device. It's a serviceable appliance. You need to be able to turn off all sorts of power to that charge controller in order to service it. So you need to be able to turn off the PV array input and also the battery connection in order to have the controller not have a source of energy that could cause a shock if you're servicing it. In an outback system, the battery breaker is typically the GFDI breaker. Other systems put the GFDI.
Brian, we're going to have to wrap this up. We've hit our 10 o'clock mark here. So we're just going to get to maybe 2 questions, if that's all right.
Sure, that's okay. And we'll make this presentation available to everybody.
Yep. Yeah, we'll be posting this on YouTube next week, and we will be sending out the presentation to everyone who completes the survey. So don't forget to do that. And we'll just get to 2 questions here. Brian, can microinverters be used on an off-grid system?
That's a good question. Yeah, they can be used in an AC coupled application, but the efficiencies are really low. I wouldn't recommend doing that. Enphase is coming out with their own version of what they call an AC battery, which is essentially a battery with its own microinverter on it. So that's one possibility. They're aiming that as a grid-tie backup system. I don't think the efficiencies are anywhere close enough to the standard off-grid systems to really recommend that at this point. So the short answer is no. The long answer is yes, but with limitations.
All right. And our next question, are there different reasons to choose modules with different amount of cells for off-grid systems?
Well, you want your PV array to always be at a higher voltage than what the battery is. So even a 36 cell module is going to have a peak power voltage of somewhere around 17 or 18 volts, which is much higher than what a 12 volt battery would need because there's losses in the system and there's effects of heat and whatnot. But other than that, no, not really. I mean, if you look at say a string of 3 60-cell modules in series, well, that's 180 cells in series. It doesn't really matter that each package is only 60 cells. You're really creating a string that's 180 cells in series. And that's just, the higher the voltage, the more efficient it is to transport it through wires, for instance, and then the MPPT controller can convert that energy right down to battery voltage. I hope that answers that.
Great. All right, well, thanks everyone for joining us. Once again, please complete that survey that will pop up after you leave the webinar and will also be in the follow-up email. And we will be posting these on YouTube next week, so feel free to subscribe to that channel to be notified. And thank you again, Brian, for the presentation.
Well, thank you, Hannah, for doing all the legwork to get this going. And sorry, folks, I wasn't able to get through the whole presentation, but we got through most of the important points. And thanks for joining us.
All right. Have a great weekend, everyone. Bye-bye.